11.3, the binomial theorem. So it says with a partner, but you're going to do this before you come to class. Okay, so Pascal's triangle. At the very end of this package, you should have a Pascal's triangle. It's something that looks like this. It's called Pascal's triangle. And this is rich with many different patterns. And so there's just a couple things I want you to do to see if you can find patterns, and you might find additional patterns as well. Okay, the first thing it asks you to do is cover all the multiples of 7 and tell me what you notice. Okay, so maybe grabbing a marker or a little piece of paper, I want you to cover all the multiples of 7. So 7, 21, 28, all multiples of 7, and there's a whole bunch of other multiples of 7 you're going to see on here. Okay, cover them up and there's some sort of pattern. I skipped the first step I asked you to do, which was to make the next row. Okay, so there's this row. Looks like we always have a 1. How would we find this next term right here? What do we seem to do to create the next row? You might see some sort of pattern. So when you come in, I'd like to see one more row. I know you have to write really, really tiny, but one more row of Pascal's triangle. Okay, just so I could see that you know how to do it. Okay, so then it asks you to cover all the multiples of 7. What do you notice? Then cover all the multiples of 5. Well, the multiples of 5 are easy to find. When you cover all the multiples of 5, what do you notice? Are there other multiples of 5? You might notice some patterns when you cover the multiples of 5. And then similarly, it gets you to cover the multiples of 3. What happens when you cover all the even multiples? What do we notice? Okay. Next question it asks you to do is determine the sum of each horizontal row. What pattern do you find? So horizontal means straight across. So when I add each row, that's 1, 2, 4, 3 and 3 is 6, 7, 8. What sort of pattern do you notice as we keep adding? What does it keep going up as? Okay, next question, it asks us to read number 5 on page 537. I've already written this row. It says we need to express using combinations. I'll give you a hint of what this starts. 1 is the same as 5C0. 5 is the same as 5C1. 10 is the same as 5C2. So how do you think we could express the rest of these rows? And that's what we're going to notice here is this Pascal's triangle has the same patterns that we see as combinations. Okay. Finally, before you come to class, I want you to expand each of the following. So x plus y squared means we go x plus y, x plus y. Multiply them together, well, we get x squared plus 2xy plus y squared. Okay. Same thing with cubed and fourth. I want you to expand, paying special attention to the coefficients. So this is 1, 2, 1. And maybe we saw that pattern somewhere. How do the coefficients of the expansions compare to Pascal's triangle? So we're going to find a really quick way that we can expand binomials. So that is what I would like you to have done before you come to class.